हेलो डियर स्टूडेंट्स, हाउ आर यू ऑल। उम्मीद है ਤੁਸੀਂ ਸਾਰੇ खुश होवोगे और जोर शोर नाल अपनी पढ़ाई कर रहे होवोगे। सो आज का टॉपिक मैं लेके आया वो है मैग्नेटिक इफेक्ट्स ऑफ करंट और 10-15 मिनट मेरे नाल जरूर स्पेंड करो और ਤੁਹਾਨੂੰ सारा चैप्टर बिल्कुल फिंगर टिप्स से हो जाएगा। सो टू अंडरस्टैंड मैग्नेटिक इफेक्ट्स ऑफ करंट means current can produce magnetic field. So we consider an experiment known as Oersted Experiment. It consists of a magnetic needle with stand and lying in its geographical north-south direction when it is free, and a straight wire lying above the needle. Now, experiments show that when there is no current through the wire, there is no deflection of the needle. Means deflection of the needle is zero. But when current is passed through the wire in the direction south to north, then north pole of the magnetic needle gets deflected towards west and south pole gets deflected towards east. That is, needle gets deflected and it aligns in the resultant field direction as shown in figure number 2. Now when direction of current is reversed, that is from north to south, then the same needle gets deflected towards north pole of the needle gets deflected towards east instead of west, and south pole gets deflected towards west. Means direction of deflection is reversed when direction of current is reversed. So this proves that whenever a current is flowing through a straight wire, it produces magnetic field around it, and because of the interaction of two magnetic fields, one due to wire carrying current, another due to magnetic needle itself. So due to interaction of these two magnetic fields, needle gets deflected, and direction of deflection of the needle gets reversed when direction of current is reversed. So to remember the direction of deflection of the needle, remember the word snow. It states that if current is from south to north, wire is over the needle, then north pole gets deflected towards west. So we can find direction of deflection of the needle knowing the direction of current. Or we can use Ampere's swimming rule to know the direction of deflection of the needle, which states that suppose you are swimming above the needle and you are facing toward the needle, and current is such that it enters at your feet and leaves at your head. Then north pole will be deflected toward your left arm and vice versa. So word snow and Ampere's swimming rule is used to remember the direction of deflection of the magnetic needle when current is passed through a wire placed above the needle. And this experiment proves that any wire carrying current produces magnetic field around it. So this is magnetic effect of current. Now, magnetic field is produced due to wire carrying current. Now what is the magnetic field? So magnetic field means it is the region or space surrounding a wire carrying current or a magnet within which its effect can be felt. So that region is called magnetic field. It is noted by B. Usually we note the magnetic field by B. Now, what is magnet? Because magnet also produces magnetic field. So magnet, any material which attracts small pieces of iron, nickel, cobalt is called a magnet. And magnets are of two types, natural magnet and artificial magnet. So natural magnet like lodestone, also called magnetite, or black iron oxide, which occurs naturally, and its structural formula is Fe3O4. So this is known as a natural magnet. An artificial magnet like bar magnet, electromagnet, horseshoe magnet, which are made by magnetizing soft iron core or steel. So there are two types of magnets. Bar magnet is an example of artificial magnet. Now, bar magnet has two poles, north pole and south pole. How to find these two poles? Take a compass, small compass, put compass just at one corner, note the direction of deflection of the needle, mark 2 points on both sides, similarly on other ends, then join these 2 points. The point of intersection of these two lines or point of intersection of these two lines is known as a pole. One is called north pole, other is called south pole. So bar magnet has two poles, north pole and south pole, which lie inside the magnet near its ends. It means magnetic length, which is known as distance between north and south pole, is always less than the length of the magnet itself. Bar magnet has attractive property. It attracts iron, nickel, cobalt, and this attraction is found to be maximum at these poles, north and south pole. It has directive property. When a bar magnet is suspended freely like this, it aligns in a particular direction known as geographical north-south direction. And the end which points toward geographical north is called north pole, and end which points toward geographical south is called south pole. So in this way we can find north and south pole of a magnet. Like poles repel each other, unlike poles attract each other. North and south poles always exist in pairs. Well, an isolated north or south pole can never exist. सगी नाल परांदा रहिंदा नाल कुड़े. So north and south pole हमेशा इकट्ठे होंगे. So then magnetic lines of force, or what are the magnetic lines of force produced by a bar magnet? So to understand magnetic lines of force means it is an imaginary continuous curve which always start from north pole, comes to south pole, out in the outer field of the magnet, and from south to north inside the magnet, as shown in this figure. So magnetic lines of force will be like this: north to south in the outer region, and inside south to north. They form closed loops. That's why no monomagnetic pole can exist. So magnetic lines of force are continuous closed loops. Two magnetic lines of force can never intersect each other, because if they intersect, then there will be two directions of motion, which is impossible, because tangent to the magnetic line of force at a point gives the direction of magnetic field at that point. So if two lines of force intersect, there will be two directions of motion, two directions of magnetic field, which is impossible. So two magnetic lines of force can never intersect each other. They are closed continuous curves. The tangent to the curve at any point gives the direction of magnetic field at that point. Moreover, magnetic lines of force contract lengthwise. Like there is north and south pole, they contract lengthwise. They are longitudinal. It indicates force of attraction between unlike poles. Moreover, they exert lateral pressure. When we have two north poles approaching each other, so magnetic lines of force exert lateral pressure, which indicates the force of repulsion between the like poles. Magnetic lines of force are always perpendicular to the surface, magnetic surface. If there is a plate, surface plate, and magnetic lines of force will be always normal to the magnetic surface. So these are some characteristics of magnetic lines of force. Then we come to magnetic field due to a straight wire carrying current. Now, magnetic field due to straight wire carrying current. Suppose we have a straight wire carrying current in the vertically upward direction. Because we have proved by Oersted experiment, any wire carrying current produces magnetic field around it. So, how to know the magnetic field due to straight wire carrying current? So, suppose a straight wire carrying current lying in the direction of current upward. Then magnetic field will encircle around the wire in circular concentric loops, and direction of magnetic field is given by right hand thumb rule. Now, what is right hand thumb rule? Hold the wire carrying current in the upward direction in your right hand, so that your thumb points in direction of current. Then direction of your fingers wrapped around the wire will give you direction of magnetic lines of force, that is magnetic field. So magnetic field will encircle around the wire like this. So magnetic field due to straight wire carrying current encircles around the wire carrying current. It means magnetic lines of force are concentric circles having wire at the center, and direction of magnetic field or magnetic lines of force is given by a right hand thumb rule. Very simple. And more is the current through a straight wire, more is the magnetic field, and more the distance of the point from the wire, less is the magnetic field. Magnetic field produced by straight wire carrying current decreases as we move away from the wire carrying current, and is maximum just at the surface of the current. Then magnetic field due to a current loop. Now, instead of straight wire, suppose we have a current loop like this. Now, suppose this loop carries current in the clockwise direction. This is the center of the O is the center of the loop, and R is the radius of the loop. Then again, since wire carrying current produces magnetic field around it, so this loop will also produce magnetic field around it like this everywhere. So it means magnetic field produced by this current loop will be maximum at the center, and its direction is given by again a right hand thumb rule. Very simple. So remember right hand thumb rule. Curl your fingers of right hand like this, and so that thumb is stretched, and now put your fingers in the direction of current like this. So this thumb will give the direction of magnetic field. So if current is in the clockwise direction in the loop, then magnetic field will be directed inward, normal to the plane of the coil. Similarly, if we have magnetic field current like this, so magnetic field will be upward. If current is clockwise, it will be downward. So we can find direction of magnetic field using right hand thumb rule. Also, whenever there is coil, it behaves like a magnet. So direction, north pole or south pole depends upon direction of the current. For example, if it is clockwise, current to the coil is clockwise, having large number of turns, then this is the clockwise direction. It will make south pole. So from the letter S, so it will be clockwise, so it will be a south pole. And if current is anti-clockwise, it will be a north pole. So it means direction of magnetic field is from south to north. So we can remember north, south pole, how they are produced in a coil carrying current. Then magnetic field due to a solenoid. Solenoid is nothing but a copper wire wound on a certain frame, well insulated from each wire, and the length of this frame is very large as compared to diameter of the frame. So solenoid is just like in the form of a helix. So its shape is like a helix, and the purpose of the solenoid is to produce uniform magnetic field. well within the solenoid. And this uniform magnetic field is used to magnetize magnets made up of soft iron or steel. And when a magnet is placed well in a solenoid carrying current, then it is known as an electromagnet. So this is the solenoid having large number of turns which are well insulated from each other. So current enters at this point. So current is like this. At this end, left end, current is clockwise, and at this end, current is anti-clockwise. So it means this end becomes south pole, this becomes north pole. So inside, direction of current will be from south to north, and outside, because it just behaves like a bar magnet, and lines of force can be shown like this: north to south in the outer side, and in the insides of the solenoid, lines of force will be from south to north. So solenoid is a device that is used to produce uniform magnetic field inside the solenoid, and magnetic field is uniform. Length of solenoid should be large as compared to its radius. Then force on a current carrying conductor. Now we have proved a wire carrying current produces magnetic field around it. We have calculated magnetic field due to a straight wire carrying current, magnetic field due to a current loop at its center, and how we can know the direction of magnetic field due to straight wire as well as due to current loop, which is given by right hand thumb rule. Now, if we place a straight wire carrying current in an external magnetic field, then it will experience a mechanical force, and the direction of mechanical force is given by Fleming's left hand rule. So suppose this is y-axis, this is x-axis, this is z-axis. Means x-axis is pointing normal to plane of the board directed toward u. Suppose magnetic field is acting along y-axis. This is external magnetic field, and conductor or wire carrying current is lying along z-axis. That is, direction of current is along the x-axis and pointing towards u. Again, direction of current or wire through a wire or conductor is pointing along x-axis, that is toward u, perpendicular to the board. Direction of magnetic field is along y-axis. Then direction of mechanical force experienced by the conductor will act along z-axis, and this direction is known by Fleming's left hand rule. Now what is Fleming's left hand rule? Stretch your left hand so that first finger, middle finger and the thumb all are mutually perpendicular each other. Now if first finger points in the direction of magnetic field, central finger points in the direction of current, then thumb will give you direction of magnetic force. This is known as Fleming's left hand rule, that is used to find direction of force experienced by a straight wire carrying current placed in a magnetic field. So from this diagram we can see it like this. So this is magnetic field, current along the x-axis toward u, then thumb gives direction of magnetic force. You can see it clearly. Fleming's left hand rule, first finger magnetic field, central finger direction of current pointing toward u, perpendicular to the board along x-axis, and magnetic force experienced by conductor is given by along z-axis by the thumb of the left hand. So this is Fleming's left hand rule. So we have studied two rules today, right hand thumb rule and Fleming's left hand rule, which are very, very important to find direction of magnetic force and direction of magnetic field or current in this chapter of magnetic effects of current. Now, why this mechanical force? Why this mechanical force acts upon the conductor? Because wire carrying current produces magnetic field, its own magnetic field, and there is also applied magnetic field. So both the magnetic field interact. So because of interaction of these two magnetic fields, so conductor experiences a mechanical force, and this mechanical force is maximum when conductor is perpendicular to the magnetic field, and this force is given by F is equal to BIL. Derivation of this relation is not in your syllabus, so F is equal to BIL. So more is the magnetic field, more is the magnetic force. More is the current flowing through the conductor, more is the magnetic force. More is the length of the conductor, more is the magnetic force. So this is all about magnetic effects of current. So it is very easy, and if you have understand, well and good. If you have not understand, then please go through this video 2 or 3 times. You will understand each and everything. So stay tuned for next new video. Thank you. God bless you all. Sat Shri Akal.